I don't have the scrolling text on the bottom because I didn't know what to call this, so I'm just gonna, yeah, there we go. Can you see the Zoom thing popping up on the top of my screen? Okay, that's fine. I am recording. It's not recording through Zoom. It's recording just onto my computer here. On OBS, yeah. Okay, I have to, yeah, still give me just 2 seconds to get the textbook open. Shoot. Let's go tab. Yeah. Turned out okay. My textbook isn't loading. Oh, now it's loading. Okay, nope. Yep. I guess I'll go and I guess I'll go for about an hour, I guess. We'll see. Yeah, my textbook isn't loading though, so I can't access anything. Do you think maybe someone could send me the textbook questions? Because this happens sometimes with my thing here. Let me. Oh, yeah. Okay, I'll just open in Chrome then. Yeah, just end this task. Ah, yes. That's what's happening. Let's see, Google Chrome. Okay. Yeah, it opened now. Good. I do have to figure out what page I'm going to, but that's fine. Or can someone find that for me? What page I'm going to? Like that? Where does the first question start for chapter 17 problems? And I'll also start a search, but maybe someone can find that first. Yeah. This is annoying that this isn't working. Try one more time. Okay, it's working now in just Adobe Acrobat Reader, so I'll just do it from there now. Okay, we're good. So it's chapter 17. Yeah. PCS for this midterm? No, I have not. Today was going to be the first one. So yeah. Okay, so we're here now. So yeah, the first suggested problem is number 1 from the practice problems of chapter 17. Oh, also I have my notes, which I will put here. I have that my PDF of the notes. I'll put that. I have no other way of sharing that except through FYE. I don't know if there is a way for me to share it through Zoom. I should probably move that away. Putting a file. No, it doesn't look like I have. It doesn't look like I'm able to. Yeah, so if I'm putting it in the FYE Discord, FYE PCS 125 homework help Discord. There it is. In Tuesday. Hey. Join FYE. If you're not on FYE, yeah. There you go. No, they didn't. They just left, and everybody asked for me. So I'm... yeah. How many things did I get? What? Sorry? Oh, I got 9 or something. 9 is what I saw, but maybe more after I was actually there. Yeah. Yeah. Okay, let's get into it. Question 1 is here. So there is question 1. So 2 waves on one string are described by the wave functions, those two, where x and y are in centimeters and t is in seconds. Find the values of the sum of the 2 waves at these points and at these points. Remember, the arguments of the trigonometric functions are in radians. Okay, so we just have to find the sum of 2 sine waves. Also notice that one is a cos wave, one is a sine wave. They have different amplitudes. So let's see. Hold on. Let me either find the trig identity or just find the exact formula that's here in my notes. Either one will work really because it's kind of the same thing. So these the fact that they have different amplitudes is... Well, I mean, yeah, I could just add them, but then... So y1 plus... But that's not really simplified in any way. y1 plus y2 would be 3 cosine... That's a terrible cosine. Cosine... Yeah. Oh, so I guess... Minus 2t. Oh, I guess... Well, they don't really... Yeah, okay. They don't really have to, but we haven't learned how to... Yeah, we haven't learned how to actually do it with, like, all of the things different. So, yeah, we actually just have to plug in these points. So this is a kind of ridiculously easy question, but x is 1, t is 1, so it'll be 3 cosine... let me write it a little nicer. Cosine 4 minus 1.6 plus 4 sine 5 minus 2, which is 3. And whatever that is, just plug it into a calculator. And B and C and so on. I think, is it okay if I just keep going? I think that's all you need for this question here. You just plug. Yeah, anybody speak up here. Either unmute or I will have... I will have or like type in the chat. I'll have the screen open. So let's look at the next one then. So next one is number 2, which is these two, or these two. You'll see what I mean when I say these two in a second. So that is this. So 2 pulses have different amplitudes approach each other with a wave speed of 1 meter per second. Oh, and the question is, well, I don't have to do every detail, but sketch the waves at 2 seconds, 4 seconds, and 5 seconds, and 6 seconds. So what would happen? Okay, so 1 second, if this is at t equals 0, right? This is at t equals 0. At 1 second, well, it would be like that, right? It would be there. Okay, in 2 seconds, it would be like that. 4 seconds, so 4 seconds later would be here. So 4 seconds later would be like this. Okay, then 6 seconds later, well, they would kind of like, it would be like this, but that's not actually going to happen. So they would add together point by point. So it would just be, if this is twice as tall. Sorry, is someone saying something? They're very quiet. I can't tell if they're asking me something. Oh, yes. Oh, no, it wasn't a question? Okay, no worries. So then they would add together like that at 6 seconds, right? Because it would be effectively this plus this, which is adds to that, right? Does that make sense? And then the question after is, what if the pulse on the right is inverted to be upright? Then how would that change? Well, yeah, it would change because then this would end up being, when they collide at 6 seconds later, it would look like that, right? Terrible drawing, of course, but that's just how it is. Yeah, up here, this one. Well, all it was asking for is it's saying, find the new wave that's created when you add them together, y2 plus y1 plus y2. What's that new wave? You don't have to find a whole formula for it. Just what is its height, or find its what is it? Find the values of y1 plus y2. So this is y1 plus y2. Find the value of y1 plus y2 when x is 1, t is 1. That would be this. When x is 1, t is a half. I didn't even write that, but it would be, you know, 3 cos 4 minus 1.6 times a half, 4 sine 5 minus 2 times a half. You just plug the values in exactly. You don't have to actually combine these waves in any way because we don't know how to do that mathematically. It's probably more complicated than we know. So, right? Yeah, that's it. It's deceptively simple. So, okay, that's number 2. Let's move to number 7. It's good to do these questions just to make sure you have a good gut feeling about how these things work. So 2 sine waves on a string are defined by the wave function that and that. Now notice this time they have the same amplitude, but different other numbers, where x, y1, and y2 are in centimeters and t is in seconds. What is the phase difference between the 2 waves at the point 5 centimeters and that? the phase difference. Phase difference. Okay, what is the positive x value closest to the origin for which the two phases differ by pi at pi? Wait, what is the? Oh, at 2 seconds. At that location, the two waves add to 0. Okay, so the first, yeah, sure, yeah, okay, that would be useful. So what is the phase difference between the two waves at 5 centimeters and t equals 2 seconds? So I'm gonna have to fix one of these numbers. So I guess I'll fix t equals 2 seconds, right? Because I can't, I can't, but it's not easy. Yeah, and I'll fix t to 2. Right? So it's going to be y equals, oh, I'm not in decimals. Y equals 2 sine 20x, and then y, or minus 32 times 2. I think the phase difference, okay, we'll deal with that in a second. Minus 32 times 2. Y equal, yeah, go for it. Mm-hmm. Makes them equal. That makes sense to me. Yeah. But what would that R2? We don't know R2 or R1 though. That's for like a physical situation that's happening where you have the two distances, R2 and R1. It's just talking about this equation here. Yeah. And with that would be the why is it n lambda? Let me see. Yeah. Yeah, so we essentially just, wouldn't the phase difference be the same regardless of the time? Why does the time and the position affect the phase difference? If the waves are, okay. Okay, let me finish the graph here. Okay, the graph is a little bit, let me fix this. Should be going to -1 to 6. And there. Here's not the best, not the most useful graph, but here's between 3 and 6. So that's it between 3 and 6. The blue one is, the red one's the first one, the blue one's the second one. So we're looking at 5, so it's fixed at 2 seconds. So at 5, which is right here, what is the phase difference between them, right? So like right here, what is the phase difference between x, t is fixed at 2, yeah. So let's see the chat. Yeah, yeah, so I just need to find, yeah, if I just plug this in, what's going to happen if I just plug this in? I'm going to get the height of the graph at both of those places, which isn't going to be that helpful, right? Because the height of the graph will just be whatever that value is, whatever that value is. Oh, and you can just find, okay, so yeah, so let's just plug it in. Y1 is going to be 2 sine of, so it's going to be 20 times 5 minus 32 times 2, close bracket. That is going to be some constant, so maybe let's figure out what that is now. Sine of, well, let's just plug this in. That's in total, everything's 36 in there? 36, okay, thank you. And then y2 is 2 sine 25 times 5 minus 30, nope, minus 40 times 2, and maybe could someone find, thank you, sine 45. So is the phase difference 9 then? That doesn't really make sense. 9 what? 9 radians? That's not. Okay. So I will add 9 here. Not quite. If I add 9 to the other one, add 9. Oh, yeah. Okay, so I'll add 9 here again. Oops. So at 5, no. But if I add 9 to this one at 5, yes. Yes, actually. They actually intersect there at 5 now. Yeah. That's it. So they... Whoop. I have to use a different mouse. Right, but right here it does intersect. It shows an intersection, right? So since it does intersect, then we're good. It was weird, yeah. But there you go. So the answer is 9 because, so delta phi equals 9, or, well, delta phi equals 45 minus 36, which is 9. And there you go. Okay, now part B is what positive value x closest to the origin, what is the positive x value closest to the origin for which these two phases differ by pi, plus or minus pi at t equals 2 seconds? Well, then we just say, in general, so if I say y1 is 2 sine, we're looking for x, we're saying t is fixed at 2, so it's going to be 20x minus 32 times 2, right? 32t, so 32 times 2, right? And the other one is y2 is just, what was it, 2 sine 25x minus 40 times 2, right? So now that we have 40 times 2, now that we have this other thing here, right, this other phase here, well, we just want to know the phase difference. So the phase difference would be 20x minus 64 minus 25x minus, it should be like that, 25x minus 80. We want that to equal plus or minus pi. Can't you? So just say pi. That's what you're saying? Just say pi here. So, yeah, okay. At that location, the two waves add to 0. If they add, whatever, that's fine. I guess that makes sense. So we have here, and now I think I just solved for x, so it's going to be 20x minus 25x. Yeah. Well, because, well, there would be two solutions. What is the positive x value close to the origin for which the two phases differ by? Okay, sure. Unless someone has a better explanation as to why there's no plus or minus. Yeah, okay, let's just say plus or minus for now. And then it's going to be negative 5x but we don't know if that the negative might be necessary to make the positive answer. I don't know. We'll see. Just leave it for now. Anyways, yeah. 16, so plus 16 equals plus or minus pi. And then, of course, so I'll just x equals plus or minus pi minus 16 over negative 5. So are those the answers? Let's see. Is it a whole number solution or is it not a whole number solution? That's the question. Minus 16. Does anybody have the answers open? Okay. Yeah. So this is right. Right? Because, right? That's what you're saying. This is we're not doing it to make a mistake here. This will still get the right answer. Yeah. Okay. So my first answer is 2.572 centimeters or something. Let's see. What is it? Unitless? No, not unitless. Wait, that should be. No, unitless. And this is also unitless. Yeah, this, but I mean this as a combination. Yeah, but the x itself is in centimeters. Yeah, x is in itself is in centimeters. I meant this, like 20x is unitless because this is 20. The units of that is over x, right? Because it has to be in a sign. To be in a sign, it has to cancel, right? So that's my first solution, and my other solution is that one of the answers in the book. My other answer is 3. Well, so then there's only one answer. So that's the answer there. How? Yeah, hold on. How? -5 on the bottom here. Yeah. No, I know. Okay, so not this. Okay. Then we're missing the fact that it says at the end here, at that location, the two waves add to 0. So let's maybe look at... Oh, did I close Desmos? No, I think I left it open here. Yeah. -16, but yeah. It does, like, it does this one minus this one. But it's not the answer in the book, so it is not. It wants the I should add these two together. Let's just see what happens when I add these two together. So that's f of x. That's g of x. Yeah. Okay, here. Okay. Like so I kind of cut out that. So 2 pi k, and then you choose a k. Oh yeah, 2k plus or minus 1 times pi. Yeah, okay, I see. And choose a k because it's the odd multiples of k, odd multiples of pi. 5 pi? How would you know to make a k of 2? You just keep incrementing. So 5 pi, 5 pi, 5 pi, and that will give me the answer. 0.0584. 0.584. Asked for what is the positive x value closest to the origin for which the two phases differ by plus or minus pi at t equals... But we're saying the phase difference is... because 1 lambda, yeah. Let me see this for a second. Okay, so we got the answer by choosing 5 to be the coefficient in front of the pi here of the phase difference. So this, to explain quickly, this is just the phase difference. This is delta phi, because it's the difference in what we get when we plug it in. Technically, it's actually negative delta phi, because I did this one minus this one minus this one. But so then I equated that to 5 pi and then solved for x. What value of x gets me that? 5 pi, because pi got me 2 point something, which is too big. But then minus pi got me this. But that doesn't really matter. That's okay. If I chose 3 pi, what would it get me there? Let's see. 1.31. And 5 pi got me the answer. And then 7 pi got me something that's further in the negative direction. But this has a phase difference of 3 pi. This isn't the... What I'm a little confused. Okay, because it's the odd multiples of pi. They're 2 pi away. Okay, that makes sense, actually. Yeah, that makes sense. They're 2 pi... Yeah, the phase difference... You're just adding 2 pi there, so that's still a phase difference of pi. Just plus 2 pi, but plus 2 pi is one full way around the circle, so it doesn't change anything. They should add to 0... Yeah. Yes. Uh, 0.0584. 84. 84. Yeah. Yes. I'm just adding the waves just to see that if it works, and then so 2 times 0.0584. Yeah. It got me a coefficient of 5, but that k would have been, in this case, k is 2. Yeah. Oh, I see. Okay, yeah. Oh, and then minus 1. And minus 1 here. And then yeah, so 3k minus 1. I mean, 2 times 3 minus 1 is 5. And then you choose that. Yeah, I see. Okay. All this is saying is that we want, like, if it was 2k times pi, right? That's like, so if k is 0, well, if k is 0, it's 0. If k is 1, it's 2 pi. Then it's 4 pi. Then it's 6 pi. These are all multiples of 2 pi, right? But we want multiples of pi, right? Like, not like, we want pi, 3 pi, 5 pi, 7 pi. These are all places where the phase difference would be pi, right? Because this one here is just pi plus 2 pi. This one's pi plus 4 pi. This one's pi plus 6 pi, right? So what we care about is that all these ones have a phase difference of pi. Right. Yeah. Sorry, I do that a lot. So all these ones have a phase difference of pi, right? And so then these ones don't. These ones have a phase difference of 2 pi. So to get the top one, you do 2k times pi. To get the bottom one, you do 2k minus 1 times pi, right? Because then if k is 1, that's 2 minus 1 is 1 pi. Right? So if we want to get the odd multiples of pi, this is how you get the odd multiples of pi. That is, I'm looking at my notes here. I have it in terms of lambda. Yeah. Oh, yeah. That's true. Yeah, exactly. So the only time that you have complete destructive interference is when the two waves are out of phase exactly by half a period, right? They can be out of phase by less than half a period, but it's not perfect destructive interference. Oh, to get phi, I just got it from the equations. Like these delta phi. Right? I just set t equals to 2. And the phase difference is going to be this one minus this one, but I did this one minus this one because I just did it backwards. They have the same amplitude, but not the same frequency. Different frequency, right? So that's why it's more complicated. So we got the phase difference. We knew the phase difference had to be some odd multiple of pi, right? Because it said that it was two phases differ by plus or minus pi. So it's an odd multiple of pi, right? So what odd multiple of pi gets the x value of this expression closest to 0? Well, it's 5 pi. It's an odd multiple of pi, right? So 5 pi is what gets this expression closest to 0. Exactly what x value is that? It's this x value. You could do that, or you could say, I want x to be 0. Let's just say I want x to be 0. What value of k can I get? So set x to be 0 here. Solve for k. You're going to get a real number. You're not going to get an integer. But then just choose the closest integer. And then you get the k value there. So does that make sense to everybody? I know that was a confusing question. Had to take a few minutes to get that, but hopefully that made... Well, because we don't have perfect destructive interference exactly at 0. We have it at 0.0584, right? So if we did have it at 0, it would give us a perfect integer, right? It would give us an integer there. But since we don't have it at 0, it's just a little off. Yeah. Okay, there we go. Thank you. That's right, yeah. The next one I have is a standing wave question, and I circled it, so that means I couldn't figure out how to do it just by looking at it. So let's see how it goes. It's another one of these ones with the phase difference and everything. So let's see if we can, put our heads together. Two waves simultaneously present on a long string have a phase difference delta phi between them, so that the standing wave formed by their combination is that, just the standard phase difference, or a standard combination of standing wave. So despite the presence of the phase angle phi, is it still true that the nodes are 1/2 wavelength apart? Yes, the nodes should be 1/2 wavelength apart. think. Yeah, don't see why not. Yeah, yes. The answer is yes. They're always 1/2 wavelength apart. Could someone? Yeah. K is K. So, there we go. And are the nodes different in any way from the way they would be if phi were 0? Well, I can show this graphically that it's not, but yeah, I guess I'll show it graphically, and then maybe while I'm showing it graphically, we can try to think of why. Let me say 2a sine kx plus phi over 2 cosine w t minus phi over 2. And hold on, why is this not working? Oh, this is oh wait, t is, wait, hold on. No, I can't graph this. I'm thinking of something else. What am I thinking of? I have t, I have x and t. Those are both independent. Sure, but then I just have a sine wave, which isn't what I was expecting to use to demonstrate here. So what is the question? Are the nodes different in any way from the way they would be if phi were 0? Well, let's see if phi were 0. If I fix t equals 0, or no, t equals 1, I guess. And then I say phi, we don't, where are the nodes? The nodes are, oh, okay, no, this is the standing wave. Yeah, this is just the standing wave. Okay, good. Never mind, that makes sense. There's the nodes. If I move phi, so it looks like the nodes are moving. So if I say here, phi is 0, and then I say, are they still at 1/2 a wavelength apart? Well, one wavelength is that, and yes, they are still 1/2 wavelength apart, right? The nodes are still like that. Are they different in any way from what they would be if phi were 0? Well, let's say they're at a different position, for sure. They're at a different position, but they are not at a different distance apart or anything like that, right? The wavelength is constant, yeah. Like the distance between the peaks is constant, yeah, and the distance between the nodes, right? And yeah, and the period is constant. There you go. So that's the difference. Is that good enough as an answer, I guess? Okay, good. Let's see the next one. Next one's number 11. So a standing wave is established in a 120 centimeter long string fixed at both ends. The string vibrates in 4 segments when driven at 120 hertz. Determine the wavelength. What is the fundamental frequency of the string? Okay, so I'll draw it. We have a string fixed at both ends. It vibrates in 4 segments. So what I assume that means, it means this, I guess. Is that's 4 segments? Or would this is 4 segments? Okay, sure, yeah, there. So then, okay, so it's the length of the string is 120 centimeters long, fixed at both ends. The string vibrates in 4 segments, driven at the frequency is 120 hertz. Okay, this is the 4th harmonic because there's 4 things. There's 4 antinodes fixed at both ends. Determine the wavelength. What is the fundamental frequency of the string? Okay, so the fundamental frequency is going to be the 1st harmonic, and the wavelength, well, we can find that by looking at, give me 1 second, I have to find the formula. There we go. So we know that we know that lambda n equals 2L over n. right? So, well, the fourth wavelength of the wavelength of the fourth harmonic is 2 times the length over 4. Yep, that makes sense to me. So lambda 4, which is what we're looking for, is L over 2, which is going to be 60 centimeters. Lambda 4 is 60 centimeters. Could someone check if that's right? And then determine the fundamental frequency. The fundamental frequency is, well, Fn. The nth harmonic is Nv over 2L. Okay, so the first harmonic is V over 2L. I don't know V. I don't know anything else about the chord, so let's see. What can I find? Can I V equals F lambda. Okay. V equals F lambda over 2L. We don't, isn't this the same F though? Or no, the speed in the string doesn't change. So we can use this pair, this pair. I think the pair. I think just using the pair is fine. Using a pair like that'll work, right? Because it's of the speed of the wave in the string is only affected by the tension and the mass density. That is not changing here, right? That is not changing here. So by changing the harmonic we're talking about, F lambda should still be V. F lambda, right? So if I say V equals F lambda, right, for any n, that's true, I think. Let's see if that works. So it's going to be the fourth and the fourth. So we just have now that the first harmonic is 120 times 60 over 2 times 120. That's in centimeters, though. So I guess I'll do... that's also in centimeters. So I guess that'll cancel. And this is just... Yeah, centimeters and centimeters will cancel. That's fine. Yeah. Dividing the frequency I have by 4. Would that always get you the answer? Yeah, I guess it would. I don't see why not. Yeah. Yep. Okay. That would also be probably simpler. So yes, that makes sense. Yeah. This makes more sense to me because you can see we're using this formula. I'll pull a spring or I'll put a box. And we move it to, we're looking for the first harmonic, so n is 1, and then what's V? Well, V we find using the fact that V doesn't change. Doesn't change when F and lambda changes, so we can choose any pair of F lambda, and that'll get us our V, so we put our V here. And we know those values, so we found it like this, and 30 hertz. Okay, and that's it. There's A and B for number 11. Any questions? I have not had the chat open, so if anybody's asking questions in the chat, then my phone number? Okay, sounds good. So let's carry on. The next one is going to be this is number 11? Yeah, so number 12. Yep, number 12. Which is going to be another similar kind of question. So a taut string has a length of 2.6 meters and is fixed at both ends. Okay. Find the wavelength of the fundamental mode of vibration of the string. Can you find the frequency of this mode? Explain why or why not. Okay. So L is 2.6. Get out of green. Fixed at both ends. Find the wavelength of the fundamental mode of vibration. Well, lambda 1 is 2L over n, which is, so lambda 1 is 5.2 meters. There we go. And can I find the frequency of this mode? I'm looking for F1 is, well, F1 is going to be V over 2L, right? 1V over 2L. V, I don't have any way of finding because I don't know what the frequency of this is, unless there's some way I can figure that out. No. So, no. Because I'm looking for... Oh, no, it would cancel it. Never mind. That is not helpful. You're not given any other extra information. You're not given enough information to also find the frequency. Yeah. Yeah. I could, but look what would happen. So F1 equals F1 lambda 1 over 2L. And remember, we're solving for F1, but F1 cancels. And then I just have, right? Then I just essentially have this equation for where n is 1, right? Where n for n equals 1, I essentially just have that equation up there. So yeah, so no, I cannot find the frequency. Is that the answer? I know there's no textbook answer for this one. Maybe could someone find the I don't know, the Slater one while we're looking? Okay, I'll keep going, but yeah, hopefully that's right. Next one's 13. Of course, anybody can stop and ask me questions. We just don't have enough information to solve it. The question is even asking, can you find it? Can you find the frequency of this mode? Explain why or why not. So, no, you cannot. And because you're just not given enough information. Okay, a string that is 30 centimeters long and has a mass per unit length of that is stretched to a tension of that. Find the fundamental frequency and the next three frequencies of possible frequencies of possible standing wave patterns on the string. Okay, well, we just used Fn equals nv over 2L. We're looking for the fundamental frequency, so it's F1 equals v over 2L. Well, we have L. V is the square root of the tension over the mass density, or mass per unit length. So we have that. So square root of the tension over mu over 2L. I have all these numbers. Just make sure everything's good. So 30 centimeters, I'm going to put that as 0.3 meters. And everything else, we're good. So I'll just plug that in. Square root of 20 over 9 times 10 to the negative 3 over 2 times 0.3. Whoops, 2 times 0.3. So I got the fundamental frequency is 78.57 hertz. And find the next three frequencies, I can't say that word for some reason, of possible standing wave patterns on the string. It's just multiples of this. It's just some n in the front here, right? So that was 1 times this. So this will be 1 times this. So then F2 is going to be 2 times 2 times F1. And F3 is going to be 3 times F1. And F4 is going to be 4 times F1. And there you go. There's the next 3. Right, because it's just a constant multiple n in the front. That's just like the counting. So I can just multiply that, and there you go. Just for the first one, n was 1. Okay, good. That's that. That's number 13. Let's move on to number 14. Of course, anybody stop me if there's any questions. The next one was a tutorial problem with this, and I spent some time trying to figure. Anyways, let's give it a try. In the arrangement shown in this figure, an object of that mass hangs from a cord around a light pulley. The length of the cord between point P and the pulley is 2 meters. When the vibrator is set to a frequency of 150 hertz, so the frequency is 150 hertz, the standing wave with 6 loops is formed. 6 loops, as in 6, 2, 3, 4, 5, 6, yeah. What must be the linear mass density of the cord? How many loops, if any, will result if m is changed to 45 kilograms? How many loops, if any, will result if m is changed to 10 kilograms? Okay, that's fine. Not bad. So what do we know? We essentially know the tension in the cord because we know the mass of this guy, right? We don't know that we're looking for the linear mass density. So essentially we're looking for V, right? Because V is the square root of T over linear mass density. That's our target. So I need another equation to help me find V, right? So we know that it has the sixth harmonic. It's doing the sixth harmonic. So F6 is 6V over 2L. Do we know how long it is? Yes, we do. We're pretty much there. We know this frequency. We know L. We know V, kind of, because we know V is T over mu. We don't know mu, but we know T. So that's only one unknown here. So F6 equals 6 square root of T over mu over 2L. And now just rearrange for what's it called? Mu. There we go. So I'll simplify a little bit. F6 equals 3 T over mu over L. So F6L over 3 equals the squared equals T over mu. 3 over F6L squared equals mu over T. So T times that equals mu. And let's give it a try. I know everything here again. So T is, T is mg, right? Because the force down here is mg. So assuming it's not moving, the force of tension will counteract that. So it's also mg. So I can just write that. Right? Should be clear here. T equals mg. And now I know everything. So I can say that the mass is 5 kilograms, so 5 times 9.81 times something squared. So it's 3 over F6L. F6 is 150 times L. L is 2. So that is going to be 4.905 times 10 to the negative 3 equals mu. Let's check the units. So this is, let's say this is kilograms meters per second squared. 3 over per second squared. That doesn't look too good. Let's see what happens. What am I trying to get? Kilograms per length? Yeah, because length is going to be meters. Oops. Oh, no, that's okay. Never mind. We're good. We're okay. Meters squared. Right, so it doesn't matter. 1 over. The 3 doesn't have a unit, so it's fine. Or unless it does. No, it doesn't. So yeah, this is fine. Because this will be... Is it fine? It is fine. Okay, we're good. Kilogram meter per second squared times second squared over meter squared. Open the chat. And then this cancels, and we just have kilograms per meter. And that's what mu is. It's kilograms per meter. We're good. Okay. So there's that, assuming that's right. I don't know if that's right. This is being recorded, by the way, if anyone's wondering if it's being recorded. I saw someone saying that in the chat there. So yes, it's being recorded. Oops. That here. I'm trying to get to the chat again there. Okay. there's that question. Let's move on. And of course, anybody ask me any questions if you have any questions. So that was 14. So 15 is this one, which also I remember being weird. So let's give it a try. Yeah. Oh, yeah. No, I just forgot about it. Yeah, let's give it a try. I just forgot about it. Yes. Hi, hello. So, sorry, I didn't hear what you said there. Sorry, what was it? Yeah. Thursday. Sure. Sounds good. Sounds good. Thank you. Great. Okay. Bye. Thank you. I'm trying my best. I have to plug in my headphones because, of course, my headphones are dying. So give me 1 second because I can't hear anything. Like, I can hear something still, but they're about to die. Which also happens constantly. Let me change my... I think it's... Okay, someone was in mid-sentence there as I started hearing, so could you say that again? Yes. I don't have the link to this. Could someone put it on the Discord? Put it on PCS, yeah. Yeah. Yeah, fair enough. Exactly. Which is somewhere in between Springer and just virtual advising room. Somewhere in between there is me there. Okay. PCS discussions. All right, there I'm there. Yes, Adam did take over, and very good. Oh, nominate me for what? Oh, okay. I will gladly give my whatever. Sure. I guess I'll message. Can I message? Can I message you after? Yeah. I was already gonna do that. You don't have to ask for it. Yeah. Don't worry about it. Exactly. Okay, I'll send that to you after. Okay, after the session, or should I do it now? Okay, sounds good. So let's see here. Oh, I close the chat again. So this one here, a sphere of mass m 1 kilogram is supported by a string that passed. Yes, question. We didn't finish. Sorry. I'm a little, yeah, okay. How many loops, if any, will result if m is changed to 45 kilograms? Okay, that's not bad. So to do that, I essentially need to, what happened? Where am I? This is the other question ended here. So I need to take the fact that this is the 6th harmonic and just, we're looking for how many loops will result, if any, if m is changed. So I think we just make this the nth harmonic. And then I don't know. Hold on, because we don't know what n is. Oh no, I guess we do, because we know that the 6th harmonic is... We know that... No, we don't know the 6th harmonic. Oh, okay. Oh, that's constant. And I just want to find, so that's the same frequency. I'm solving for n. N is the number of loops, is the harmonic that is. Yeah, I think so. Because then I can just, so what I'm saying is that I take this, I say, we know F, I'll rewrite it down here. So I take that, I know that Fn is n v over 2l, and more specifically, I know this is n square root of t over mu over 2l. The frequency stays the same. The mass is changing. Mass is here. So Fn equals n square root of mg over mu over 2l. So now I know that the frequency stays the same. The only thing that's changing is the mass. So I just set the mass to, I know this, I know this, I know this. I just set the mass to a different number and then solve for n. That's what I'm going to do. So let's see if that works. This is going to be n equals 2l fn over square root mg over mu. Right? Hold on. Yes, that's right. And then now I can just set m to a different number, m to 45, and then 10, and see if it does anything. I don't know. See if it works. So 45 first. So 2 times L was 2, right? L is 2. Times 150, right? 2 is the, 150 is the frequency. 150 over, yeah. Mu is constant. Yeah, mu is constant. We just solved for that here, yeah. Times 10 to the negative 3. So I got exactly 2. I got n equals 2. So what that tells me is that when you put a 45 kilogram mass on it, you get the second harmonic. And then if you put a 10 kilogram mass on it, so this is with 45 kilograms, bad, and n with a 10 kilogram is, well, I'm just going to change the number 45 to the number 2. To the number 10, I mean. Can't speak. Well, I got 4.24, which is no harmonic. No harmonic. Between the 4th and 5th harmonic, but no harmonic. And yeah, there you go. That's B and C. Does that make sense? Good? Sounds good? Yeah. 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 Because you can't have 4.24 antinodes, right? The harmonic is counting the antinodes, right? Maybe if you're really close, I guess it could just be like a number error, but this is too far to round. Yeah. So, okay, now we're good for number 15. A sphere, is number 15 one of the suggested problems? Yes, it is. Okay. A sphere of mass m equals 1 kilogram is supported by a string that passes over a pulley at the end of the horizontal rod of length 0.3 meters. The string makes that angle with the rod. The fundamental frequency of the standing waves in the portion of the string above the rod is 60 hertz. Find the mass of the portion of the string above the rod. So let's highlight the important information here. So start with the mass is 1 kilogram. Again, what that gives us really is the tension, right? Because it tells us how hard this is pulling down here. L is 0.3. Theta is 35 degrees. The fundamental frequency is at 60 hertz. Find the mass of the portion of the string above the rod. The mass of the portion of the string above the rod. Okay, not bad. So, yeah. Sure. Don't worry. Well, because the question is just asking is how many loops, if any, will result if m is changed to 10, right? Loops is like, that's a loop, right? How many? So you only get a standing wave. You only get a standing wave to begin with when you're, let's see it here. On a string fixed at both ends, you only get a standing wave if the frequency if this is true for some n, for some integer n, right? This is the equation for the nth harmonic of a standing wave. It comes from the fact that you need to have the length of the string to be a multiple of lambda over 2 and lambda over 2, right? So, although I don't really know how to get from this to this, but maybe if I thought about it for a second. It has to be a whole number. Yeah, it has to be an integer, right? So if it's not an integer, it's between the fourth and fifth harmonic, but that doesn't look like anything. That doesn't look like a standing wave yet or anything like that. It's just yeah. No problem. No problem at all. Of course, I'm happy to go back. Don't worry. So, okay, I'll move on now. So a sphere of mass 1 kilogram, yada, yada, yada. So what we know from here, we're essentially just using this formula again. The nth harmonic is nv over 2l. We're looking for the mass of the portion of the string above the rod. Okay, well, how do we find that? Well, like, it's a little weird. What we can do is we can say, well, we need the mass density. The mass density is the mass over the length, right? The mass over the length. We almost know this length. We don't quite know it. We know this length, but we can find it because we know the angle. Well, mass density is the mass over the length, so V is tension over mass over length. Okay, then this is equal to N times the square root of, well, it would be T length over M, right? Over 2L. Watch that these are different L's here, right? Well, I can now just solve for M, right? And to be clear here, this is the mass of the string, right? Mass of the string, mass of the string, right? So Fn is equal to N square root of T. Now what's T? T is the mg, but big M, right? Big M G L over mass of the string over 2L. And now we can just solve for mass of the string, right? So 2 times the length, the frequency of the nth harmonic, over n, square root, well, I guess I'll just square it, I guess, equals mgl over ms. I hope I did that right. Yes, I think I did. Good. So ms is what we're looking for. So I just do, it'll be, so mgl n over 2lfn squared equals ms. I'm doing a little bit too much algebra in my head there, but yeah, that I did that right. That's good. Okay, and now I just solve. I just plug in values. So capital M is 1, G is 9.81. Lowercase l is going to be, what's lowercase l? This is lowercase l. So to solve for that, well, it's going to be 6. So cosine theta is adjacent over hypotenuse, right? So what that tells us is that L is big L over cosine theta, right? If I'm looking for this L here. So I can just plug that in. So mg big L over cosine theta, right? Then it's just n over 2lfn squared. I know probably some the L's can cancel, but I'll just leave it. It's okay. Is ms, and now we're good. So 1 times 9.81 times a fraction, which is L is 0.3 over cosine of the angle in degrees. Let me put my calculator in degrees. The degrees is 35 times something squared, and the something is n. N is 1. It tells us that the first fundamental frequency, the first harmonic, is 60 hertz. So it's just 1 over 2 times 0.3 times Fn, and Fn is F1, which is 60. And I got a mass of 2.772 times 10 to the negative 3 kilograms. And let's just check that. Let's check the units here quickly just to make sure that we got this right. So m is in kilograms. This is in meters per second squared. Meters over nothing. Nothing over meters squared. Okay, so the meters cancels. And Fn is per second. The theta came from here. So we need to find the cursive L. We don't want big L. We want cursive L here, right? Because that's the length. So cosine theta is adjacent over hypotenuse. So cosine theta is big L over cursive L. So cursive L is big L over cos theta. Does that make sense? To Dahlia. Yeah. But the tension in the string is T. And that's the same here and here. You wouldn't do it for the string. You wouldn't, no, you don't do it for the string. You don't need the, we know the tension in the string is the tension here, is the same tension like this. Yeah, it's not the same as that, yeah. Lowercase l is because of this here. The mass density is the mass per length of this top part here, right? So we're looking for the mass of this top part, so we need the length of the top part. We don't need the length of here. We need the length of the top part here. So that's why I needed that, to have this cursive L. That makes sense, right? Yeah. Okay. The units don't. Oh no, they do work out. Never mind. Always like for a second I'm like, oh my god, they didn't work out. We did something wrong. Those cancel. Those cancel. We get kilograms. So yes, we're fine. Okay. I'm gonna trust that this was right. I can check the answer in the textbook. So let's take a look. Maybe I shouldn't be so quick to trust that it was right. Okay. They got 1.86. So this is in. Okay. Then I probably did something wrong. Let's see. Yeah. Maybe some units are off. Yeah. Yeah, go for it. So you solved for. You have to find mu. Maybe I might have just typed something in my calculator wrong. Let's just see. 9.81. Okay, let's see. Well, we definitely have it, like, was L equal to, little L equal to L over cos theta? So then L here, yeah. This L, was this L supposed to be different? Yes, this L is supposed to be different. This is the wrong L. It's not, this is not vibrating. This is vibrating. So this, yeah. Okay, so then this should also be cursive L, is the problem. This should also be cursive L. Right, because that's the length that's vibrating. So I will cancel here because that'll get more complicated if I don't cancel. So, okay, units work out, that's fine. Good, no units work out. Now, this is cursive L still, and this is cursive L. So I'll distribute the squared in. Okay, I'll distribute the squared in. Now, one of these cancels with one of these. I mean, I don't actually have to do all this work. Like that was the problem. Now we'll get the right answer, but a little bit easier to write. So now I have a different expression for ms. So mg n squared over 4, and this is going to be capital L over cos theta fn squared equals ms, and this should get the right answer because now I have a cosine in the numerator technically if I do one more step. Right? Yeah. So that was the problem. I just that was the wrong m. So 1 times 9.81 times 1 squared over 4 times the fraction 0.3 over cosine 35, was it? I think, times 35, and the frequency is 60, times 60 squared. So I got 1.86 86 grams. There you go. So that was the problem. Good thing we checked that. We should check more. Yeah. Okay, any questions about this one? Yeah, exactly. That's not the length of string, right? That's just the length relating to the string, which we could find the length of string from that. Right, but that wasn't. I hear you, yeah. Yeah. Yes. That's good. So you could also find mu. You could also just find mu separately and then multiply L by that, the little L, and you would find the same answer. Which is just turning this into ms equals mu L. And essentially then all the rest of this except the L, which is, well, here I guess. So all the rest of it is 1 over mu. Anyways, whatever. It worked out, so it's okay. Yeah, no problem. Okay, number 16 is, I think, the same question but in general, which is that. So I did it already. Yep. It's the same question but in general. I could just get rid of the n. N is 1. So you just get rid of the 1, and then this would just be f. And then that's everything. So yeah. Let's see. Okay, is that good? Did I skip that one then, since I already did it? I'll move on to 17. This is the answer. This general formula here. This is the answer. Does that make sense? Okay, how about we do one more question, then I'll just take a break for a bit, I guess, because we can keep going. I'll just take a break for a bit after this question, and then we'll keep going after that. So let's do number 17. A violin string has a length of 0.35 meters and is tuned to concert G with the frequency of G being 392 hertz. How far from the end of the string must the violinist play her finger to play the correct concert A, with the frequency of A being that? If this position is to remain correct to 1/2 the width of a finger, that is to within that, what is the maximum allowable percentage change in the string tension? Okay, this looks complicated. So, okay, L is 0.35 meters. We know that it's tuned to FG, which means I think that means the first harmonic is 392 hertz. I think that is the first harmonic. I think. So how far from the end of the string must the violinist place her finger to play concert A? Yeah. But I don't think it'll matter that. Yeah, I mean, yeah, I don't think so, because what's happening is just that it's when they say it is tuned to that frequency, I think that just means if you don't put your finger on it and you pull the bow, what frequency does it play? It plays 392. Right? So that's what the first harmonic, pretty much. The first harmonic, right? Yeah. So FA, which is our target, or something, I don't know, I'll just call it FA, is 440. 440 hertz. If this position is to remain correct to 1/2 the width of a finger, that is within, so correct to plus or minus 0.6 or 0.06 meters. Oh no, sorry, it's 0.6 centimeters. So that's 6 centimeters. So 0.6 centimeters would be that. I mean, meters. There you go. What is the maximum allowable percentage change in the string tension? Okay, so the change in the string tension. Well, okay, let's start with part A, I guess. Part A is separate. So how far from the end of the string must the violinist place her finger to play that frequency? So I want the new Fn to be... Is it a harmonic? Okay, yeah. Yeah. L2 is L1 minus X. X is what we're looking for. The distance, how far from the end of the string. So Y 0.6. Oh, that's for part B. So I don't know. Yeah, let's probably is important somehow, but yeah. Go for it. What am I solving for? X here. I'm solving for X here. Right? But then we're saying that this is the second harmonic. They're saying that this is the second harmonic. Right? Okay, and that's equal to NV over... But then that would be the first harmonic. Oh, okay. So it's still the first harmonic? Okay, so then still say that, and then 2L2. And then take the ratio of these two. So it's F1 over F2 equals L2 over L1. And what am I trying to find? This is 1. The frequencies are the same. No, the frequencies are not the same. Sorry. They're different. But we're trying to solve for L2. But and then just solve for X. Just solve for X. Yeah. So I'll just solve for, you know what, I'll put this in the equation and then solve for X right away. F2 equals, so that's L1 minus X over L1. So I'm solving for X, right? So it's going to be L1 F1 over F2 equals L1 minus X. So it's going to be X equals L1 minus L1 F1, L1 F1 over F2. So X equals, okay, L1 is 0.30, well, whatever. I'll just plug it into my calculator, see what I get. 0.35 meters minus the fraction L1, 0.35, times the first frequency, which is 392, over 440. So I got X is 0.04 meters. So 4 centimeters. 417. 4 centimeters. Yeah, okay. Yeah, I just, I ran it. 38 meters. Yep. So 3.8 centimeters. That is the answer. So let's recap quickly what we just did, because it's a little weird what we just did. So a violin string is this long. Its natural frequency, without putting any finger on it, if you just pull the bow across it, it's 392 hertz. How far from the end do you have to place your finger, right, to play a 440? To play 440. So what we know is that we know a frequency, right? We know a frequency is this at the length, at the specified length, right? So we know for both of them, we're calling it the first harmonic. I don't know if it really matters if you call it any harmonic. It just matters that it'll be the same harmonic. So let's just say for both of them, we're calling it the first harmonic. Even though I'm calling this F2, I just mean the second F, not like the second harmonic. I just mean the second go around. So in the first frequency is that natural frequency 392, right? L1 is that total length of the string. So V over 2L1 is that first frequency. Okay. The second frequency is going to be V over 2L2, right? And what we're looking for is X here, which is how far, if this is our string of length L1, and let's say I have to put my finger here, the new length of string is going to be L2, and what I'm looking for is how far from the end did I have to put my finger. So what that means is that L2 is L1 minus X, which is true, right? So I take the ratio of these two. I know that F1 over F2 is going to be just this divided by this is going to be L2 over L1. You can do the algebra to see that. And I sub in what I know. I know that this is true, right? I know that this is true. So I do that, solve for X, and I get the right answer. So any questions about that? F, right? Yeah. Yeah, is the length. V is going to cancel, and 2 is 2. So that's not changing. Yeah. Exactly. Okay, so then if this position is to remain correct to 1/2 the width of a finger, that is to that, what is the maximum allowable percentage change in string tension? So let's say, I think we have to put it to the maximum. We have to put it to the maximum. So that would be plus this. So this is X equals 3.8, centimeters. So let's just add 0.6 centimeters to it. So X max, the maximum place you can put your finger is at 4.4 centimeters. And we need to solve for the second tension, I guess. What is the maximum allowable percentage change? Because T1 is going to be, I can solve for it here. In fact, I'll do it now. So this is for part B. So F2 equals the square root of T1. Oh, no, sorry. This is maximum allowable change in tension. Why is the string tension changing? So it's solve for T here. Oh, we don't know the mass density. No, we don't know the mass density. Yeah. So I'm isolating for T. Is that T1 or T2? That's what I'm confused about. That's T1. Because T2 is what happens when we're at this length, when we're at X max. Or am I wrong about that? That's my idea. Does someone have a comment on that? Yeah. 4L2 squared. Sorry, equals. Just the equals there. So, okay, this is just going to be 4 mu L2 squared F2 squared is the first tension. And the second tension is just going to be L2 plus 0.6. So this is our first equation. Let me write it nicer here. So T1 is 4 mu L2 squared F2 squared. And what I'm thinking is T2 would be 4 mu L2 plus 0.006 squared F2 squared. And I'm just trying to solve for... What am I solving for? I'm solving for the ratio here. Oh, yeah, I guess T2 over T1 is what I need. So I'm going to do T2 over T1. So T2 over T1. Yeah, okay. So that's 4 mu L2 plus 0.006 squared F2 squared over 4 mu L2 squared F2 squared. So So this ratio is L2 plus 0.006 squared over L2 squared. L2, do we know L2? We can find L2 pretty fast. L2 is L1 minus X, right? Is that right? L2 equals L1 minus X. L2 equals 0.35 minus 0.0338. So what did you say? Yeah. 0.31. I got 312, so yeah, very good. Meters. So now I just have to this would be in meters here. Yeah. Don't worry. Yeah. That's the length of that's L1. We got that from the question. Yeah. L1 0.31. Yeah. So then, don't worry. So this is 0.312 plus 0.006 squared over 0.312 squared. And then we have 0.312 plus 0.006 over 0.312 squared. So I got that the ratio T2 over T1 equals 1.0388. So it's a 3.88%. 3.88% increase. Or just like plus or minus 3. I guess it's just plus or minus 1 plus or minus 3.88%. So 3.88% is my answer. 3.85% is the answer. So we're good. Yeah, we're good. Okay, there's that question. That does seem like a test question. We're definitely going to have to take a ratio of something in the test, I'd say. You're going to have to do this ratio thing, where you see two situations where almost everything's the same, except like you're just changing. There's something changing that you know what is changing, which is these frequencies, and there's something that you're trying to see how much something else changes, but it's the same situation, and so you just take a ratio in that case, and that'll help you find it. You mean here T1 over T2, or you would get it. You would get a different answer because you're not that's like saying, like if you got 25 out of 30 on the test, is that the same thing as getting 30 out of 25? They're related, but it's not the same number. Yes, it is. Okay. Thank you, Manuel. Thank you. Well, I want to know how much bigger is T2 than T1, right? So that's how I know I put T2 on the numerator. I'm comparing T2 to T1. Like you're comparing the score you got to the actual amount possible on the test. You're not comparing the amount possible on the test to the amount you got, right? Oh, because 100, if I got 1 as an answer, that means it wouldn't change. There would be no, you couldn't, you'd have to be 100% accurate if you got 1 as an answer, right? But if I got 101%, that means I have 1% wiggle room here, right? So since I got 103.88%, that means I have 3.88% wiggle room to do here. And that's what the question was asking. It was asking, what is the maximum allowable percentage change in the string tension? Right. So again, if I got 100%, the change would be 0. Right? But since I got 3.88%, that means the maximum allowable change is 3.88. Yeah. Which yes. Yes. Yes, of course. So we know that we have a violin of length L, a string of length L, which is 0.35 meters. It's tuned. If you don't touch your finger anywhere on it, you just pull the bow, you get 392 hertz as the frequency that's out of it. So the first question is, how far from the end do you have to put your finger to get 440 hertz out of it? So notice here, what's happening is that we have 2 things that are changing. One thing that we exactly know how it's changing, the frequency, right? The frequency is changing in a way we exactly know how, and we're looking for how does the length change? How does the length of the string change, right? Where do you have to place your finger on the string? So the first situation can be modeled by this. F1 is 392 hertz, and it's equal to first harmonic. First harmonic is V over 2L1, the total length, right? So that's going to be true. And then the same situation, although slightly different, can be modeled by this. F2, which is not the second harmonic, but just the second frequency that we're talking about, is going to be, still call it the first harmonic. So there's a 1 up here. I don't think that really matters what we call it. I think it'll cancel out no matter what. Doesn't matter what harmonic we call it. So we have, in fact, well, I'll do it after I finish explaining. I'll see if it works for another harmonic. It will. So we have here now that it's equal to V, the same V, over 2 times a different length, right? 2 times a different length. That different length is defined by this, right? The second length, which is after you put your finger on it, it's the original length minus however far you moved your finger down from the top, right? So this is kind of describing that. So I can take the ratio of these 2 events, right? F1 over F2 is equal to L2 over L1. That's just a ratio of these 2 things. And it's here that you can see that it doesn't matter what harmonic I chose. The ratio would still be this. So as long as they're the same harmonic, it doesn't matter. So I chose them both to be the first harmonic. It doesn't matter. We both get this ratio at the end anyways. So, well, from here, I can just plug in what I know and solve for x, which is the distance down from the top. And I solve for this value for x. So does that make sense for part A? Good. Okay. So then part B is asking what is the, so if the sound is right to within half a finger width, 0.6 centimeters of adjustability, what is the maximum allowable percentage change in the string tension? So what that means is, what is T2 over T1, where T2 is at the max, so the max allowable, so I'll say x plus or minus 0.6 centimeters, and this is at exactly x, right? That's down here. So if I hit it exactly, or I hit it at, I press my finger at exactly the maximum allowable error, what is the ratio of that change in tension? And that'll be the maximum allowable percentage change in the string tension. So I need to find T2 over T1. So I need an expression for T1 and T2. So I use this formula, right, which is that Fn is n times v, but v is that, over 2L2. This is for the second situation, right? And then same thing here, although... Oh yeah, same thing here. I just solve for T1. I just solve for T1 in this. So does that make... It's a little bit messy. If it's too messy, I'll rewrite it. But does that make sense? I take this and solve for T1. And then T2 is if I'm exactly 0.06 off of where I'm supposed to be. So L2 is exactly where I'm supposed to be, plus 0.06, or 0.006 meters, is exactly the maximum allowable error that I can do. And I want T2 over T1, so I take T2 over T1. A lot of stuff cancels. I know L2. I can solve for L2 using what we said before, which was that L2 was L1 minus X. I know X, I know L1. So I just solve, and I get 1.0388 as the answer. T2 over T1 is 1.0388, which means I have 3.88% is the maximum allowable change in tension here. So did that make sense? Okay, good. Sounds good. No problem. Okay, let's take a break. Let's take about a 10-minute break, I guess, and let's see how we do after. What question are we on? We just did number 17, so we are halfway through chapter 17 stuff. And luckily, chapter 13 stuff is pretty short, so we probably will finish everything, including tomorrow's session. Of course, not today, but we'll finish everything, including tomorrow's session. All the textbook practice questions. And yeah, we'll go from there. Okay, so 10-minute break. I hope the AFK thing will work. There, can I do that? Can everybody see? Did that work? Okay, I'm not back at 38, but I'm back at 45. There. Sure, yes, okay.
No, but like actually, because
Yes,
it's for the...
I know. Yes, I will give it to you.
I don't know. Ali, are you in here? Is Ali still in here? No. Okay. I don't know if we need your phone number, cause like, if a lot of people are gonna do it, I don't know if it's in your best interest to just give everyone your phone number.
Yeah.
So maybe we don't have to do
you
that.
don't need to enter their phone number or their student number. They're not required.
Oh, you don't.
But like,
you don't have to.
we should probably at least do the student number.
Yes.
We won't do the phone number.
Email is probably the best.
Yeah.
Okay, should I just put it in the chat? I guess I don't mind giving people my email and student number, so I'll just put it in the chat. Okay.
I'll put an announcement as well. I mean, you deserve it, bro.
I mean, I don't know what I'm gonna get, but I appreciate anything like this that you guys do.
It was the upper year's idea.
Yeah, really? Okay, well that's very nice of them.
You know,
That's
Ali.
nice. Yeah, that's very nice. Yeah. So there's my student number 501046722, and then my email is someone put in the chat before, but I'll put it again. Adam.
Oh, that's the wrong thing.
There, that's my email. Okay, well, I'll take a break for a minute. I'll go get a snack, and then I'll be back at 45. Okay.
The student number and email is for like an award. For leadership. I'll send a link.
Yeah, Adam does deserve like an award. Like, yeah,
Yeah, if we can't pay him, if we can't pay him for the tutorials, at least we could do that.
Oh, wait, what's the word for it? Is it like a scholarship or is it just like?
I don't know, but it's probably big.
Is it like official? Is it like school
Yeah,
official?
it's a res thing.
Jeez, and then
And that's probably good for like Ryerson awards too, like actual like big ones, you know.
There's a link somewhere in the chat. I don't know how far up to the actual form.
I'll send it after. It's probably way too far up.
Are you guys talking about like that email that we got sent for like if we think someone's like we can nominate people, that one?
Yeah, it's that one.
So everyone here should nominate Adam.
Yeah,
Yeah, he
and
deserves it.
me, just for being cool.
Adam is very cool though. Okay,
Where's the link?
if you guys want me to like, if you guys need me to like complete the form, I just complete the form to nominate him.
Normat form.
At what time tomorrow is he like doing this?
It's on Discord. I don't know. It's like 6, 7, something like that.
Right. Okay. Good
It's
to
in
know.
the Twitter announcements. So the way I said. And he's also gonna have something on Thursday.
On Thursday too?
Yeah, but it's for MTL, not for this.
It's for
Yeah. So
yeah.
usually what happens is he sets a schedule. Every Thursday we have an MTH one to prep us for the mini test. And this is done on the FYE usually, but like for this circumstance, it's very special because we got this Zoom link. So if you want to like, if you're like kind of like enjoying this kind of style of studying and all that, and you're not in the FYE, I would highly suggest you join the FYE because there is a lot of benefits in joining the server as you can get helps from other students and you can get to know more people. So yeah, definitely look into that, guys.
I don't even have to plug. This is great.
Yeah, you literally you overthrew the whole study hall into basically one big promotion. Like this is like a trial, like this is like a free trial type thing. But
Yeah,
it's
this is
already
Adam
free.
does
It is
this.
free. but
Adam
it's-
does this all the time in the FYA server, and he does it for physics, for math. I think he did it for ECN and for CPS maybe.
Yeah, he
Yeah,
did
yeah.
a lot
Adam is
of
the big
those,
boy,
and
but I mean,
we also
maybe
got other
like
people
an
like
FYE.
Yeah, we also have
here. Mhm.
other
So
tutors. Not
um
Edsel though. Edsel's not a
Manuel
tutor.
can link the FIE server in the chat. Pretty easy process. When you do join and you're in verification, just at me, at
Oh, yeah. It's
and I will
Is
verify
that
you.
me? Yeah, is that me?
big man promoting for the server. Jeez.
Yeah, hopefully I get a promotion medal.
Yeah, this man just wants mod.
Wait. Oh, promotion.
Just add that in the server and you're good. You're good to go.
Number. Just join the server. Just be like, hey, we're from the study session with Adam.
No,
Exactly.
yeah, here's the link to the Discord server.
Someone's plugging.
So essentially, we have a lot of other tutors, like including myself.
Yeah,
Although I am retired, but we do
Yo,
have a lot of
individual
tutors
award.
that are willing to help you right away. So yeah, great resource. Great resource.
Still sad that
Which is
Springer's
great.
computer just died. That's probably not good because I don't know if he's going to be able to do lectures.
He will. He will. He has
He-
another
he
computer.
said-
You just like thing.
Is tomorrow's session gonna be on Discord then?
Yes.
Mhm.
Yo, let me nominate Adam. Maybe Adam's gonna get
Yeah.
scholarship.
So yeah, exactly. Adam has been tutoring since Dane left. There was a little bit of a break where Robin was answering questions, but yeah.
Which year is Adam at?
He's in our year,
Adam,
which is crazy.
yeah. He spent a
What?
year. He took a year off tutoring, for grade like high school. And then he started uni again, or he started.
Oh,
uni.
so he's first year? I
Yeah.
didn't
Yeah.
hear.
He's
He's
Oh,
a bit
damn.
older
just
than
like
us, but he's first year.
Damn.
He's a king.
Yeah,
Yeah,
it's crazy.
exactly. That's
isn't
what I
it?
said when I found out that. Like, I was like, yo, says I'm like third year or something, and then someone was like, nah, family's first year. Like,
What
wait,
is
Yeah.
his
first year?
GPA? 4? 5?
I don't know.
I don't
5, yeah,
even
5 or
know.
6 maybe.
6
No,
or
bro, I think
6.
it's a solid 26.5.
I don't know, but he's so selfless and he always helps. It's crazy.
He's
And he does
legitimately
these and he
godsend.
spends hours on these things.
Yeah.
He even
He
did.
also, like,
He even did study
prepares them.
sessions when he had COVID.
Yeah.
That was.
Wait, he
Yeah,
got
he
confirmed?
did them
Yeah,
while
he got
while
COVID.
he
And he
had
said he got
COVID.
it.
Wait, was he confirmed? I know he said he's not
Yeah,
getting.
yeah, he did. He
Yeah.
did. He had COVID for sure.
Yo, I
That's
bet
why-
Adam is just like at his computer right now, just blushing. I bet he's like, damn, bro.
No, he's
he needs to
probably
get
taking a
water.
break
He's
because
probably
he's
getting
always
water or
helping.
something. Yeah.
No, bro, he probably ate and it's probably like back now. And it's probably just blushing. He's like, damn, bro, this is gonna be so nice. This is so
I mean, we tell him that we appreciate him a whole lot
course.
because we don't pay him, so he does it for free.
Yeah, for his birthday, we all got him like we all chipped in and stuff, but
Actually,
we can't pay
speaking
him.
of getting paid, this might not be available to everyone, but for math, if you have CPW, he posted an announcement saying like if you want to take notes for his class, you can get paid for it, like through like Ryerson or whatever.
Wait, Adam pays you?
No.
No. He
No.
said, no, he's saying that for CPW's class, he can like pay money for people to take notes of the class, like people with neat handwriting, because
Yeah,
CPW's
it's
notes
like
aren't
called
always
"Are
neat.
you noted?" is what it says here.
More profs should do that, especially the ones with terrible handwriting.
I don't know if it's. I don't think he's paying anyone. I think it's
Well,
like
no,
through
Ryerson does,
the university,
but
but
like
it's still a
it's
good idea.
for him.
Okay, I'm back. Hello,
We
everybody.
love you.
Adam, you're getting nominated.
Good. I guess I am for something. Yeah.
Wait, what category do I put him in? Leadership? The
Yeah,
first one?
it's the second last one. No.
Wait,
it's-
second last?
Yeah.
How about the first one? Leadership, leader of the year. No, okay, second last one.
It's called what is it called? I forgot what it's called.
Well,
Adam,
thank
you
you
are
very
a
much.
selfless person, but you should still nominate yourself.
Oh, individual awards.
Am I able
it's
to?
called the Ryerson Engineering Exceptional.
Yes, you're allowed to nominate yourself.
Okay, but
Oh,
that's
is
not-
it this? Hold on. Is it? Let me find
It's
it.
the NOR Awards.
Not this.
No.
Okay, not this. Okay.
What is that though? Can we give you that?
This is something else that someone sent me that I should nominate. This is you're supposed to nominate yourself for, I think.
Oh, you nominate yourself
Okay,
for it?
done. Adam got nominated.
Oh no, you are. It's whatever. It's either you're nominating someone or they're nominating themselves.
Go crazy, Adam.
Wait,
You're gonna be a
that's the link.
millionaire.
So which section are we nominating him for? Just
Individual award, and then it's the second last one, Ryerson Engineering.
Wait, Adam, is this recording?
thank you.
This is recording.
Is it gonna be posted on the Discord server?
It'll be posted on the Discord server. Yes.
Okay, that's good. What do you
Another
use?
shameless plug.
My YouTube channel is the plug here for that one.
Yo, go like, share, subscribe,
Yeah.
and
Can
make
we
sure.
get him the 100K plaque, please?
Oh yeah.
Yo, make sure you click the link in the description for a free 100K coin.
No,
Raise challenge
click
legend.
the link in the comment section that I posted. It's very safe.
I didn't know you were a student, to be honest. I thought you were like, honest to God, like a tutor.
Yeah.
Yeah.
Well.
Basically, yes.
Yes, can we see that? Yo, Majad and Adam collab. Can I please see that?
Majan and Adam collab.
Can I ask a question? Can I ask a question?
You can ask whatever question you like. Yeah.
Yeah. What is your GPA? GPA?
Last
Is
last semester.
Yeah.
Last
Or-
semester, the cumulative GPA was 3.67. I got 3.67 there because
Wait.
of I got a B in chemistry because I didn't like chemistry.
Yeah.
But I
Poor guy.
got 4.33 in linear algebra, so that's pretty good.
Nice.
Ooh.
Someone be
Who
getting
do I
the
add? Oh, Dahlia, I didn't verify you.
I got an A in chemistry.
No,
I got, like,
you're
B
verified.
B plus
You
rating,
have
so I
access
Yeah.
to the channels. They're on the left.
Adam is just like he's just like genetically modified. Like I swear, like he's probably has some different genes.
Maybe I just don't know.
You know, like the crisp they talk about. It's
Yeah,
like,
I'm just advanced. Yeah.
yeah.
All the people that joined are verified, by the way. You just like you should see the channels on the left. You go to role
Can I
assignment.
get verified?
Here's your discipline. So you get announcements and channels for that, for the courses and stuff like that.
Yo,
Yeah, there you go.
can I get verified, please?
No,
No,
you're
Erwin.
unverified.
Yeah, you can't get verified. I'm sorry.
Man, everyone gets verified except me.
Yeah,
Oh, come. I'm
because we don't
sorry,
like you,
man.
Erwin.
You just didn't make the cut. You just
That's
didn't make the cut.
Yeah, bro. Is it because I'm a civil? That's why.
Yeah, I don't like
Yeah.
civils.
I'm in civil too. Hey, I'm in
Hey.
civil too.
Well,
So-
that's
Alright, unverified.
Speaking of Edsel, gone. Okay,
Yo, shameless plug. Civil engineering is the best engineering.
that's just
Alright, kick him out. Kick him out.
Yeah.
Sounds exactly
He's
what
gone.
like what a civil engineer would say.
Hey guys, I don't know
Adam,
why you
thanks
got
for the session. I'm gonna go now.
Okay, sounds good. Have a good
Civil
night. Have a good night,
engineering.
Memo.
Alright, let's get back to stuff.
Okay.
Yeah.
We good to go? This is
Yeah.
question 31. So if for some reason the suggested problem skip a bunch, but yep, here's our next question. You can see my screen, right? It's all good. You can see me.
Good, everything is good.
Everything's good? Okay. So a student holds a tuning fork oscillating at 256 hertz. He walks towards a wall at a constant speed of 1.33 meters per second. What beat frequency does he observe when the tuning fork, between the tuning fork and its echo? Let's start there. So there's a guy. He's holding the tuning fork. Tuning fork. And it's vibrating at 256 hertz. So that sound is going over here to some wall. It's bouncing off the wall at, and he's observing it at some different frequency, right? What beat frequency does he observe between the tuning fork and its echo? So we need to figure out what is the frequency that's coming back at him, right? That he's observing here. So he's observing a 256 hertz frequency, but he's also observing a different frequency that's coming here because of, I'm pretty sure because of the Doppler effect. This seems like a Doppler effect question. And then to find the beat frequency, we just do F beat is the absolute difference of F1 and F2. So we know F1 is 256. We need to find the other frequency that's coming at him and then just find the difference, and that's the beat frequency. Right. Okay. So the other frequency. Yeah.
Wouldn't you use the Doppler effect to find F2 and then just like plug them in? Isn't that the way to do it?
Yeah. That sounds right to me.
Okay, I just don't know.
Yeah. So we want the observed frequency. So FO is the frequency from the source, so that must be 256. Oops, that's not a 6. The speed of sound in air is something. Let's see what it is. 333? 334, I mean? Or
343.
meters per second at room
343.
temperature.
V equals 343 meters per second at room temperature. Yeah, thank you. So 343 plus V naught, let's deal with that in a second. And then 343 plus or minus Vs. Okay. So the source, the observer is moving towards the wall at 1.33 meters per second. The source is not moving. The source is the wall here.
Sorry.
Yeah, go for it.
I think the source is moving this, like it's bounding at the same speed. So it's going back at you with the same speed. Like the distance is so small it cannot be affected.
Wait,
I
so
was-
the wall is approaching you at the same speed you're approaching the wall.
No, the echo of the sound is approaching you with the same speed that you're shouting your echo.
That
You-
speed
you
is the
shot it-
same. That's the speed of sound in air. These two speeds are the same, but
No.
Mhm.
The observer is walking 1.33 meters per second. The frequency is hitting the wall. It will rebound. The echo will rebound with the same speed.
it'll. Let me see. Let me
I think
for a
that's what
second.
I'm thinking.
Yeah,
Like,
I think
it
he's
could be
right.
wrong.
I think he's right, because
Yeah, I think he's fair.
if you're approaching the wall, then the amount of time it takes the sound to get back to you would not be the same amount of time that the sound took to get to the wall, because it leaves
Yeah.
and it returns to a different location. because you're going to be closer to the wall than when you initially released.
So what's the change I should make here?
I think it's the same
instead
speed
of
for both.
instead of 0, just 1.33. I think. I'm
Okay,
not sure.
let's try. So, this would be F.
I think the top for the 1.33 on top should be 0 because the wall isn't moving. Because I think the wall is the observer.
No, the observer is the guy.
No, but like
No.
when we have to because it bounced off the wall. So the first we have to find the frequency that the wall is observing, kind of.
Yeah,
And
that's
then
the first.
the frequency it bounces back is going to be that frequency. If that
Yeah,
makes sense.
exactly. It flips the script. So in this
Let's-
case, the top one should be 0 because the wall
Let's
isn't
try this
moving.
first. Let's try this first. If this doesn't work, then we know that one of the speeds is wrong. We can try other options. Because there's no real way to prove any of these yet. We'll just know if the answer is correct.
Fair enough.
Mm-hmm. I'm trying them. So, 343 plus 1.33 over 343 minus 1.33. Part A, what is the
And
difference?
subtract 256
Yeah.
as well.
No,
because-
this is right. This is right. What's written here.
Yeah.
So, why? Hold on. Beat frequency is beat.
It's because the observer is moving at 1.3.
No.
Because
The echo is rebounding at you with the same speed that you like. It's like a ball. If you hit a ball to the wall and it's like totally elastic collision, it will rebound with the same speed, right?
Oh no, wait. Oh no, it is correct. You just did it all in one shot. Oh, okay. I think because the way I did it separately.
You did like well how separately? Like the wall observing separately?
I said the wall was the observer, so I said the frequency that the wall will hear would be 343 divided by 343 minus 1.33, and then assign that frequency. And then I do the frequency that the person hears after the sound bounces
Oh,
off
I
the
see,
wall.
yeah.
So the wall becomes the source,
Yeah.
and then you just use that frequency, and then
Let's do that.
rearrange
I'm
the
gonna
sound.
write that. So this is method 1.
That's the same what I said.
Yeah, it is, yeah.
Oh, wait.
It's the exact same, except I did mine in 2 steps.
I'm gonna write that out because I think that makes sense. Method
2 is probably the better way to understand it anyway.
Right, that's why I'm writing it out again, yeah. So you have a tuning fork that's vibrating at 256 hertz. The sound is going to a wall. What is the wall here? Okay, sorry, you're also moving at 1.33 meters per second towards the wall. What is the wall here? Because what the wall hears is what it's going to reflect back, right? What the wall hears is what it's going to reflect back. So what does it hear? It's observing. So that observing frequency is, the frequency that it's observing is 256 times, so VFS, F from the source, 343 plus the velocity of the observer, that's 0, over 343 minus 1.33. So this is going to be the frequency that the wall hears, which is the same as the frequency that the wall is reflecting back towards the person. So let's see what that is. 256 times 343 over 343 minus 1.33. So that's 256.9965. Let's do it to a few decimals there. That's the hertz. And now that's the frequency that's coming back this way. That's our new F source, right? Is F observer, right? This is F observer 1. Call it F observer 1. That's the new source frequency that's coming out. And now what does he hear? Right, what does this guy hear? Well, he is the new observer. So the frequency of the observer 2, which is when you're here, is the frequency from the source. So I'll say this is the second frequency from the source, is F observer 1, which is 256.9965, times V plus V observer, so 343 plus the velocity of the observer is 1.33 meters per second towards, over V343 minus the velocity of the source. The source is not moving. So we get our second frequency to be 343 plus 1. Can't type. Plus 1.33 over 343, and I get my new frequency to be 257.99. Okay, and now I want to find the difference between 256 minus 257.99. The absolute value of that is our beat frequency, which is going to be 1.99.
I have a question for step 1.
Yes.
For method 1, could you screw up?
Beats per second. Yep. Okay. Method 1.
For method 1, couldn't you just like, I don't know if this will work every time, but couldn't you just say, since you're the one who produces the sound and you're the one who's observing the sound, couldn't you just logically say that you're both the source and the observer, and therefore that's why you put plus 1.33 divided, couldn't you say that? Or
You're both the source and the observer. Yeah.
But would that work? Would that be like a good way to think about it, or is it just better to just do?
Doesn't fully agree with, like, I don't know if that would work always. It would work here. You are the source and the observer. It's just
in a
that
case like this. So like in a question like this where you are like this, in a question like
Can
this.
I say something? Can I say something?
Yeah.
Imagine you're like taking a ball, like a rubber ball, and hit it to the wall, and it's like completely elastic collision. It will rebound with the same speed, right?
Yeah.
Yes.
Think of the same thing here. You hit something to the wall, it will rebound with the same speed. That's what I thought when I was solving it.
Yeah, that makes sense to me.
Yeah, it makes sense. I think as a kind of a shortcut, every time I think if you are the one who observes it, because like you are listening for it, and you are the one who produces it, I think this should work every time.
Yeah.
If you're not the one who's listening for it, and you're not the one who's producing it, then different method. But I think in this situation, it should always work.
I would still go with method 2 here, personally, because this makes more sense, like, to separate it like this. But yeah, that.
It won't work every time, because sometimes if the distance is too big, the echo will take the echo's velocity will get affected. It won't be the same as the source. I think it will lose some energy, or it will gain some energy. Something will happen.
Yeah.
So you will have to find the echo's velocity and then use that.
Yeah. I don't know, but I think they would have to give us that extra information, which I can't imagine. I don't know if they would.
I don't think they're going to give us a question where the velocity of the sound is going to change because it's too far from, like, the source.
I think the speed of sound will stay the same unless they like flash freeze it for a quick second and the temperature changes from 30 degrees to like 25 degrees.
Yeah, something has to happen. Something has to happen like that for it to change.
Yeah.
So, could you explain method 2 one more time?
Yeah, there's 2 parts to it, and I actually I want to do it in general now, so I'm going to do it in general too. So let's just say that we have some frequency from the source 1. What the wall hears is the frequency observed 1. What the wall sends back is the frequency from the source 2, and what you finally hear, which is what we're calling F2, is the frequency observed 2. So what's happening is that you are sending out a frequency F source 1, right? And the wall hears something that's different than 256 because you're moving towards it with 1.33 meters per second. Let's say you're moving, VS1 is 1.33. So let's do it in general. The frequency observed by the wall, V observed 1, is the frequency from the source 1, the original frequency from the source, times the speed of sound in air, we use this formula here, plus the velocity of the observer. Well, the velocity of the observer is 0, so it's just V, right, over, because the observer is the wall, over V minus the velocity from the source, which is VS1, right, velocity from the source 1. I guess I can just call it VS, doesn't really matter. I'm not going to have another one. This is our new frequency, right? That is our new, that's the frequency that the wall hears, which is also the frequency that the wall is sending back, right? It's also the frequency that the wall is sending back. So this equals frequency from the source 2, right? So a new source, the source is now the wall, an echo from the wall. That frequency is the same frequency that the wall heard, right? So it's sending it back. Now, what does the person hear? Well, the person hears F observer 2, right? So the second observed frequency, which is what we want F2 in this, is going to be the frequency from the source, right, which is FS2 times, the speed of sound in air plus the velocity of the observer, while the observer is moving towards the sound at v source, over the speed of sound in air minus the velocity of the source. But the source in this case is the wall, so it's 0. And now we can finally say that since this is equal to f2, this is our second heard frequency. F2 is, I'm going to just write this in full general form. So f from the source 1 times v over v minus vs times v plus vs over v. And as you see, we get what the other guy was saying. V plus vs over v minus vs.
Yeah.
And there you go. That's exactly right. So that's exactly what method 1 was. Method 1 is just getting to this final formula, doing this cancellation, right? Because these v's cancel. Oops. But just ahead of that. So then you have this here. So it's frequency from the source, all this stuff here.
This also seems like a test question.
Yeah.
Only because it involves the
It
Doppler
does.
effect in such a way that you kind of have to like
Think about it a lot, right? You
Yeah.
have to really think about it. Yeah.
Yeah, this does look like a test question, to be honest.
It does.
I agree.
Okay, so did that make sense?
Yes.
And to the person who asked me to repeat it, did that make sense?
Yeah.
I think it was wrong.
Yeah, it did.
Okay, good.
Yeah.
So we did the general term just to prove that method 1
Yeah.
is equivalent to method 2.
Yes.
Okay.
That's right. Just to show
Yeah,
that this is what we did in method 1. Method 1, and this is what we did. This is what we did in method 2, and this is what we did in method 1. And
Yeah,
you see,
method 1 and method 2 are the same thing. You just like method 1 is like you go directly to that, like logically, and method 2 like you take a couple of steps. in
you do the
between.
math and you get to that, which is one step away from method 2, right? Yeah.
Can you
Okay.
Just go a little bit up.
Yeah.
No, down.
Down
A
to me?
little down. I just wanna. Yeah, thank you.
That's good.
Okay.
Are we still doing more questions, or is it the end of?
No, I think I'll go till 9:30, and 9:30 will be the end.
Oh, okay.
Okay. So yes, more questions. Sorry, not no. Yes, more questions. This was question 31, and we don't quite have the answer. We have B to do still. Am I good to move on? Someone asked me to stay here.
The question was.
Yeah,
the
you're
answer was
good to move on.
is actually 2. I found it.
What'd you say? Sorry.
The back of the book. I said the back of the book question is the answer is 2.
Yeah, I see
So
it
we
here.
got it
I see it
first
here too. We got it. We got the first part. Yeah. So how fast must he walk? Can't read all of a sudden. Away from the wall to observe a beat frequency of 5 hertz. Well, the reason I also wanted to do it in general is to answer that second part. So we know that the beat frequency is the absolute value of f1, which is f source 1, minus f2, right? Well, we know we want that to be 5, right? The question is we want that beat frequency to be 5. So 5 equals, well, I'll just leave it as f beat. And say we want the beat frequency to be some specific number. Well, I want it to be the absolute value of fs1 minus f2. Well, I already wrote that, but f2 is this whole thing up here, right? Which is fs1 times v plus vs over v minus vs, absolute value. And we're trying to solve for vs here, right? So f beat equals, well, how do I get vs out of there? I can do, what can I do? Well, I hope
Wait,
I can.
don't we know f beat? Does it say?
Yeah, we know it's 5.
Yeah.
We know
This
it's
is what we have to do, I think. So we basically have to say beat frequency is 5.
Yeah, I can write 5 here right now, and that would be the same thing.
Okay, so
Can't we just take out the absolute value by adding plus or minus and make it? And
yeah, that's what you
duplicate
have to do. You have to say 5 equals 256.
And then just
plus or
solve for
minus
B.
whatever. And then the entire term that's not f1 is going to be equal to 261 or 251. So then you just kind of solve for that. You know what I mean?
Yeah. So put another set of brackets and plus minus here.
Yeah.
Yeah.
And
Okay.
then if it's 5, then the other term is going to be 256 or 251, something like that.
Wait, why 256 or 251?
No.
You take 250. No, because you take 256 or 261s. Because you take.
The resulting frequency has to be
It's-
lower because you're moving away from the wall. So it has to be less.
So
It's
the
just the Doppler
251.
effect.
Well, no, you're moving towards the wall, aren't you?
No, he said how fast are you? Do you have to move away from the wall?
Oh, how fast do you have to move away from the
So
wall? Okay.
you know that it's going to be that the
frequency is going to be
the
lower.
observed frequency has to be lower.
Yes, that's true. So, there you go. Any excuse to drop the absolute values. Yes, there you go. That is correct. So you're moving away, so this is going to be positive, right? This is going to be less than this, so this quantity is going to be positive, right? Let me just open the chat. Yeah, so now we just isolate for VS. So I'll do that by, I guess I'll move F beat, we'll call it FB, minus FS1 equals minus FS1 V, I guess I'll divide both sides by minus FS1 equals V plus VS over V minus VS. And then I can, what can I do? Why is this more complicated than I think I'll just plug in numbers now.
No, multiply the
Okay.
denominator onto the other side, and you get coefficients.
Oh, okay, yeah.
Because you know what V is.
Yeah.
V is a constant.
V minus VS times FB minus FS1 equals, yeah, so then I shouldn't have moved that, but that's fine. So then that's V plus, yeah, I see what I did wrong. Okay, never mind. So minus FS1 V plus VS. Okay. Then I just need to, this is supposed to be entirely multiplied, so I need to do it like this. So V, F, B. I don't have to do this in general. I could start plugging in numbers, but I'm this far in, so I'm just going to stick with it.
I also feel like you could just, in the beginning, you could have just like factored out FS1. Because
I don't know if that would have helped solving.
I don't know. I feel like I just.
Yeah, I see what you mean. Yeah, I could have.
I mean, because
could possibly have
would have
helped.
been easier.
Yeah.
Not like really easy, but just like.
Yeah, it would have changed a little bit. You're right.
Yeah.
FS1, VS. Okay, now what terms have VS? Three terms have VS in it, so I'll move everything that's not VS to the other side there. So FS1 VS. Oh, you know what? Yeah, okay, fine. FS1 VS minus, or I'll do plus next, plus VS FS1 minus VS FB equals minus FS1 plus V FS1 minus VFB. Okay.
Shouldn't that be V FS1 for the right side? Instead of having just negative, it should be negative V.
I'm just taking this term here.
Yeah, but
which
from
should
above,
be
yeah.
V. Yeah, you're right. Yeah, put a V there. Good. Okay. Factor out of VS. So VS is equal to negative V FS1 plus V FS1. Oh, that cancels. So it's just minus V FB over. What do I have? I have this. Oops. Look at that properly. That turns into just 2 times that. So then I can just. This is just 2 FS1 minus FB. I think that's right. Yep. So let's see what this is. Negative V, which is 343 times FB, which is 5, over 2 times frequency from the source 1 is 256 minus 5. I got 3.VS equals negative 3.38 meters per second. And that is correct. There we go. So negative 3.38 meters per second towards the wall. So 3.38 meters per second away from the wall. And that's the answer. Okay. So did that make sense?
Yeah. Is that gonna be it for today?
No, I still until 9:30, so still 15 more minutes.
Oh, okay.
But it is recorded, so if you want to go, you can,
Yeah, I was gonna go. Thank you.
Sounds good. Have a good night.
You too.
Wait, so for like this question, you just get rid of the absolute values.
I got rid of the absolute values because
You have to assume the lower one because he's going away from the wall, don't you?
No, because the reason I got rid of the absolute values easily is because I just asked, like, what would this quantity be? This minus this, right? So what I really want to ask is FS1 greater than FS1 with all this stuff next to it? VS over V minus VS. Is this true? If that is true, then this is going to be a positive quantity. The difference is going to be a positive quantity, so it doesn't matter. The absolute values don't do anything. Well, this is true because the frequency from the source is going to be the Doppler effect frequency is going to be lower because we're moving away from the wall in the second part. We're moving away. Right? So since you're moving away, the Doppler effect frequency is going to be lower, right? This is the Doppler effect frequency. Doppler frequency. This is original frequency. So since this is true, this is positive. I can just forget about the absolute values. Does that make sense?
And if he was moving towards the y, you would have just added negative in the front.
Yes. I would have just added a negative to the front.
And then the rest is just like algebra. Just like move that to the other side and then.
Yes, it is. It's just algebra. Yeah.
Wait just a second.
Sorry.
Wait, no, go back to the algebra part if you can, please.
Is it down here?
Yeah, down here.
Just to, I'm double checking my this thing. We do not change the signs of the frequencies because the sound waves are still like going to towards each other, right? He's moving to the back, but the total velocity is toward the right.
The positive velocity, yeah, I didn't change because I got a negative answer. So positive velocity is towards the wall. So we're moving away from the wall at 3.38 meters per second.
Okay, I see.
Right? Yeah. There you go. Okay, I'm going to move on to 32, but if anyone has any more questions, just let me know. I will do that. So while attempting to tune the note C at 523 hertz, a piano tuner hears 2 beats per second between a reference oscillator and the string. What are the possible frequencies of the string? So C is supposed to be 523 hertz. There is a beat frequency, so 2 equals, so I'm just going to use this, F beat equals the absolute value of the reference note, so the reference, whatever, minus the one heard, right? So that's the actual note C minus the one heard. So 2 equals absolute value of 523 minus the frequency heard. So what are the frequencies heard? Well, there's 2 options. It's either 2 equals 523 minus the frequency heard, sorry, that should be lower, or 2 equals the frequency, well, negative 523 minus the frequency heard, because the absolute value. So either way, we just solve. So the frequency heard is either 521 or the frequency heard is I'll just do it. I can't do it all in my head. Minus 523 plus frequency heard. So 525. Yep, someone just said that. The frequency heard. There you go. Those are the 2 options for the frequency. Does that make sense?
So it's just very simple Doppler.
It's just absolute values. We just had to take into account the absolute values. Okay, what are the when she tightens the string slightly, she hears 3 beats per second. What is the frequency of the string now? So you tighten it a little bit. And there's only one possibility now, I think, for this, right? Let me check the answer there. There's only one possibility now. We're doing 32. There's no answers for 32.
Since it's tighter.
Well, that would, if you're tightening the string, so let's look at frequency is equal to V over 2L. L is staying the same. V is the square root of t over mu. Mu staying the same. So if this value goes up, this value goes up, this value goes up, which means this value goes up.
Wait, so what's T tension?
T is tension, yeah.
Why would, like, how does tension? Oh yeah, because like tighter is like higher tension.
Yeah, right. The tighter the string, the higher the tension, the higher the velocity v in the string, right? And that brings the frequency up. So if she's tightening it, it's only going to be the higher frequency. So it's going to be 3 equals 523. No, yeah. So this is for part B. 3 equals the absolute value of 523 minus the frequency heard. So this is either 3 equals 523 minus the frequency heard, or 3 equals, or 3 plus 523 equals the frequency heard. So this is either frequency heard is 520, or the frequency heard is 526. And so we have to go, you tightened it. So if she tightened it, the frequency went up. So it couldn't have gone to 520 because that would go down from both of these original ones. So it has to go to 526. So 526 is the answer. Right? Again, she tightened it, so the frequency has to go up. Our original two frequencies were either 521 or 525. Couldn't be 520 because that would, for both of them, that would mean going down. So now the only frequency that it could possibly be is 526, and that's the frequency of the string. Right?
I'm just taking a bit back on.
Can I go back up?
What?
This is 32, yeah? Spilt water.
Yeah, it is 526.
Good?
Yep, it is.
Okay. So, let's see. The next part is part C. Someone doing dishes in the background. Could they use?
Yeah, that's me.
Oh, it's you.
Bad.
Okay, don't worry. So, by what percentage should the piano tuner now change the tension in the string to bring it into tune? So, what is the percentage change in tension? That sounds like T2 over T1, right? What is the percentage change in tension? So, what is the tension right now? Right? What is the tension right now? Well, we know the frequency right now. Frequency right now is 526. We know that the frequency is equal to the frequency. So this is for part C. This is situation 1. This is I don't know, event 1. So F1. We know that F1, first harmonic, or it doesn't matter, nth harmonic. The nth harmonic is V over 2L. Now, the length of the string is not changing, so I didn't put any symbol there. But T1 over mu, T1 is changing here, right? T1 is changing. Then in event 2, right, event 2, well, the new frequency in event 2, that's going to be the correct 253, or 523. I can't read. Hopefully I said the other numbers right. 523. And that's going to be, again, the nth harmonic, same n, the second tension over mu over 2 times the same length, right? So now I want T2 over T1. Well, I'm going to rearrange this for T1. So this implies that, this implies that, and this implies that. Come on. There you go. I'll rearrange this for T1, rearrange this for T2. So this is going to be 2L F1 equal over N squared times mu equals T1. Could someone just check if I did that right? Move that, square. That looks right to me. And this will be the same thing. So mu times 2L F2 over N squared equals T1. Sorry, equals T2. So I want T2 over T1. So T2 over T1 is going to be mu, and I'll square everything now. So it's going to be 4L squared F2 squared over N squared over T1, which is mu 4L squared F1 squared over N squared. So what cancels? Well, mu's, 4's, L's, N's. And all that we have left is that this is F2 squared over F1 squared. So now we know that the ratio of T2 to T1 is F2 squared over F1 squared. And I can just plug in numbers. I know F2. F2 is 253 and F1 is 256. And again, I cannot read. So I mean 523 and 526. So this is 523 squared over 526 squared. 3 squared over 526 squared. So I got 0.9886. What that tells me, so this is equal to 98.86%. What this tells me is that I have to loosen it by 1.36%. Loosen it by 1.36%. And I don't have the answer, but can someone check maybe?
Yeah. It is 1.14, but I would say it's
okay.
close enough.
Sounds good. Yeah, that's close enough. Right. I don't know why it's off by that much, but okay, it's fine. Whatever. So yeah, so you loosen it by 1.36%, because 98.86 plus 1.36 is 100.
Wait, no, you got the right number. I don't think that's 3.6. I think that is 1.4. Because do 1 minus 0.9886, you get 1.14. So yeah, it is right.
That is true. I just can't do subtraction. So yes, it is 14.
You have to carry us. It's like it's much weight.
There you go.
Yeah.
Yeah.
Okay, any questions about this one?
Can't we just use the? I had this question. Can't we just use the equation, like the formula, the expression that we found in the other question, the one we did like the 2 questions ago? I forget which one was it.
Like the frequency, like with the Doppler effect?
Yeah, with the violence and the.
Oh, with the violin.
Yeah, the violin one.
Here. Looks pretty similar. The thing is that length is changing here, so frequency went away. But yeah, it is the same thing, really. Why is it any different? I mean, it didn't have ends. It didn't have any ends, but that's the only. Yeah, not much change. Not much change from that question.
That's definitely a move you probably want to know for the midterm. This whole ratio thing is definitely something.
I would agree. Yes, I would agree with that. Let's see how long 34 is. If it's too long, then we'll just leave it for tomorrow.
So where exactly is the idea behind the ratio? Is it just like T2 over T1 equals F2 over F1? That's all we have to remember?
F2 squared over F1 squared.
No, but usually the ratio is not something specific. It's just something that appears, right?
Like you mean is it true always? Is that your question?
Like how exactly do you apply the ratio? Just to make sure I got it.
Well, the question was asking for by what percentage should the piano tuner now change the tension in the spring? So the changed tension, the ratio of the changed tension to the original tension.
Or so whenever it's a percentage, it's a ratio.
Yeah. Yeah.
Oh, and then it just falls into place. And this
that's going to be it for us, by the way. It's like 9:30 already.
Yeah, that'll be it for today.
And for formulas, what do you use? Do you just use the sheet they give us?
I have my own notes, so they're on the Discord. I have these notes.
Or is it like a formula sheet, or is it just like notes?
It's formula sheet. I mean, it's notes, but the formulas are all in there with a bunch of the variables. So like I have this. Let me close this. I have like this is this. So there's the Doppler effect, and it shows all the things to do with it, and then here's all these things, and there's all the formulas. I just kind of scroll through here and find what I'm looking for. It's pretty much all there. It is all there.
Just so people know, the midterm is open book. You're actually allowed to have you're allowed to have the notes open up on your computer. That's not disallowed, I don't think, because it is open book and these are notes, right?
I got a question.